And we just sort of watch as our numbers rise. Okay, we're just going to wait a few minutes while we get people entering the room, entering the webinar. Thanks for joining us this evening. Okay, it looks like folks are taking their time, and I want to be sensitive to everyone who's in. So I think we'll get started. Hi, everyone. I'm Kelly Redder, Executive Director of the Labazo Alumni House on the RIT campus. And while the house is currently closed through to July 1 and possibly beyond, we're taking reservations, and I encourage you to check out our website in the chat box as you think about your future family gatherings, reunions, weddings, retirements, business meetings, and conferences. A visit's a wonderful way to reacclimate to RIT. Many in our RIT family have asked how they can help our students and the university in light of all that's happening in the world. We're incredibly grateful for those offers. There are two ways you can help out. First, our new graduates and current students are seeking positions for full-time careers and co-ops. If your company is hiring, please contact RIT's Career Services Office and allow them to post the position in our systems. In addition, there's now an unprecedented need for financial aid scholarships for both our in-person and virtual Tiger students. In honor of our special guest tonight, we'd like to highlight the Stephen Ware Endowed Graduate Fellowship Fund. It was established in 2018 to provide graduate student support for MS and PhD candidates in the College of Science as a giving option for you. Those dollars assist with research projects and support of students participating in those areas. Note that support of these areas will be counted in RIT's historic billion-dollar campaign, which has reached the $750 million mark. If you're able, please make a gift at the link in the chat box. Thank you. Now, just a few housekeeping points. All attendees have joined in mute mode. However, your questions can be entered in the chat or question boxes at any time throughout the discussion. We'll make every effort to address all your comments and questions throughout the webinar. This webinar is being recorded and will be shared with you in the coming weeks. If you have any technical questions, please feel free to type those into the chat box as well, and we'll do our best to get you the appropriate answers. Tonight's event is sponsored by the Labazo Alumni House as part of the Club Mackenzie series, celebrating wit, wisdom, inspiration, and intellectual stimulation with your favorite RIT faculty and staff. Tonight, I'd like to introduce Joel Kastner. He's a professor on the faculty of Rochester Institute of Technology, Center for Imaging Science and School of Physics and Astronomy. He was the founding director of RIT's Laboratory for Multi-Wavelength Astrophysics. Prior to his 2 decades at RIT, Kastner spent almost a decade at MIT, first as Bantrell postdoc at MIT's Haystack Radio Observatory, then as staff scientist with MIT's side of the Chandra, then AXEF, X-ray Center, Science Center. His research interests lie in the early and late stages of stellar evolution. For example, the formative stages of stars and planetary systems and their death throes. He was conducting observations of forming and dying stars and stellar systems across a broad swath of the electromagnetic spectrum, from radio to X-rays. Kastner is lead author or co-author on more than 170 refereed journal articles that have garnered nearly 7,000 citations. He has led or co-organized more than 24 astronomical symposia and conferences. He was among the original group of roughly 230 astronomers named as Legacy Fellows of the American Astronomical Society in 2020, and presently serves as chair of the AAS Committee on Employment. Dr. Kastner, welcome this evening. Thank you so much for joining us. Take it away. Our Tiger audience is all yours.
Thank you so much, Kelly. I hope everyone can hear me okay. It's a very kind introduction. I'm going to share my slides with you now and do the always death-defying feat on a Zoom webinar of going into speaker mode. I hope you're all able to see the first slide here, which has the sort of whimsical title of my talk tonight, this evening, watching dying stars transform into butterflies and other tales of stellar metamorphosis. Hopefully the meaning behind that will become clear. And I want to, first of all, thank the students and former students, RIT's graduate students who are working with me on this program. Paula Moraga is a PhD student in our Astrophysical Sciences and Technology program. And Paula is working on the images. You'll see some of her handiwork tonight, in images I'm going to show you. Jesse Bublitz is a recent PhD graduate of RIT. He's now a postdoctoral fellow at Green Bank Observatory down in West Virginia. And Rudy Montez was actually the very first graduate of our AST PhD program. And he's a good friend and longtime collaborator of mine. Now he's been out in the real world of professional astronomy for 10 years now. And you see the other colleagues here I'm working with, my longtime friend and colleague, Bruce Ballack from the University of Washington, and two colleagues and friends from up the road, Adam Frank and Eric Blackman from the University of Rochester. I think you'll see a little of their work in this talk later on too. So, what are we talking about tonight? Well, we're talking about the secret lives of stars, the life cycles of stars more specifically. And I'll be especially talking about the late stages, the death stages of stars. And this schematic set of cartoons here, actually, which includes some real images, astronomical images, in addition to the artist's representations here, it's intended to sort of walk you through the life cycle of stars in the low mass and high mass categories. And when astronomers talk about low mass stars, believe it or not, they're talking about stars like the sun, and up to, in fact, a few times the mass of the sun, maybe 8 times the mass of the sun. Anything lower than that would be considered really an intermediate to low mass star. So you can imagine the sun is going to follow the track that you see in the upper part of this diagram. Stars form out of gas and dust. I'll try to use my pointer here without moving ahead in the slides. Stars form out of clouds of gas and dust, interstellar clouds of gas and dust that interstellar meaning they lie between the stars throughout our galaxy. Those clouds of gas and dust can become massive enough, and if disturbed in various ways, say a supernova goes off somewhere nearby, you can get compression in those clouds. And once the compression starts and the self-gravity of these large, massive clouds of gas and dust, which may be hundreds to millions of times the mass of the sun, once a chunk of one of those clouds begins to collapse, it's very hard to stop it. And a star will form. That's a talk for perhaps another time. But out of that formation process, one can get a star, say the mass of the sun, and that's what's shown here as the small yellow sphere. That's a low mass star. And we call a star when it's undergoing nuclear fusion. So a star like the sun in fact, is undergoing fusion in its core. It's converting hydrogen atoms into helium atoms in its core. And that's what powers the sun. That's what generates the sun's luminosity that we receive here at Earth. That process has a finite lifetime though. The sun has about a mere 10 billion years worth of hydrogen fuel in its core that it can convert to helium. When that runs out, our sun is going to go through a catastrophic set of changes, and that's what's shown here in the form of this red giant. Red giants are in the process of converting helium, which has been generated in the core, to heavier things, carbon, oxygen, and so on. For a low mass star, that's about where things stop. You can convert helium into carbon and oxygen, quite a bit of carbon, it turns out. In fact, stars like the sun are probably the carbon factories in the universe. all the carbon in our bodies, the things that we hold dear to life itself, were generated in stars like the sun, very likely. How does that material get back out into interstellar space so that we can enjoy it in the form of our own lives? Well, that's what I'm interested in studying and my colleagues are, when we're looking at planetary nebulae. It's during that phase, very late phase of a red giant's life, when it begins to literally get so luminous as a red giant that it begins to blow its outer layers away. And that's when you get a planetary nebula. When the planetary nebula has dispersed, basically the star has blown itself away out into interstellar space for the benefit of future generations of stars and planets and life on those planets. The center of the star, the core of the star, where the hydrogen burning, hydrogen fusion has converted hydrogen into helium and then helium into carbon and so on, that's a white dwarf. White dwarfs are the hottest stars known. They can reach temperatures that are up to 10 to 100 times, 10 to 50 times or so hotter than the sun. But they're very small. This is the core of the star. It's actually an Earth-sized, Earth diameter object at the end of its life, a typical low mass star. So I'm going to be talking about that phase of the low mass, quote unquote, star's life. And I'm not even going to talk about the high mass progression in this life cycle, because again, that would be a completely separate talk. So we're just going to focus on low mass stars. Just to give you the quick overview though, a high mass star would be generating elements that were so heavy down in its core that eventually can't hold itself up anymore. And it's going to implode and then explode as a supernova. Stars like the sun aren't going to do that. They're going to die quietly, but fairly rapidly as planetary nebulae. This is a more quantitative way to look at the same story that I just told you. You have here the progression of a star that starts out with about twice the sun's mass. So a little bit more massive than the sun, considerably more massive than the sun, but not so massive that a star like this is going to explode as a supernova late in life. And we've put the star here on a diagram that is near and dear to the hearts of all astronomers. It's called the Hertzsprung-Russell diagram. And it's a very handy way to understand stars at all phases of their lives. It's a plot of, on the y-axis over here, the luminosity of the star, and this is in log units in terms of the sun's luminosity. So the sun on this diagram would be at about 0, at precisely 0. And that quantity, luminosity, is being measured here against the temperature of the star. It's going to be plotted against the temperature of the star. The sun would lie therefore around 0, and in log units, a little bit less. The sun's surface is a little less than 10,000 degrees. So the sun's going to sit about over here in the diagram. Our 2 solar mass star that's twice as massive as the sun, starts out considerably more luminous than the sun and quite a bit hotter. It's about 10,000 degrees, 4 on a log scale in absolute degrees Kelvin. In the numbers here that you see that are color coded, that tells you in log units how long the star is going to be sitting in each of these phases in years. So a star that starts out with twice the mass of the sun is going to be converting via fusion hydrogen into helium in its core for 10 to the 9.1 years. That's about 1 billion years, a little bit longer than 1 billion years. So that's how long the fusion process takes in a star that's twice as massive as the sun. As I mentioned before, the sun will require 10 billion years to exhaust all of its hydrogen and convert it into helium. Well, by the way, we're about halfway through that. The sun is a classic example of a middle-aged star. It's about 5 billion years old. So it's exhausted about half of its core hydrogen at this point, converted about half of it into helium. So let's take the 2 solar mass star again. So after that billion years of converting hydrogen to helium, the star begins a rapid set of changes. For about another 100 million years or so, a star like that starts out with about 2 solar masses or so, 2 times the mass of the sun, is going to be burning helium in its core after all the hydrogen has been converted to helium. But after that, the star takes off, rapidly increases in size, cools off. So that's why it's going to the right in this diagram. It's becoming cooler, and it becomes a red giant. We call it a red giant because it is huge. Stars in the red giant phase can have radii, can have diameters that are about the order of the Earth's orbit around the sun. We're talking enormous stars, and you can see the sorts of luminosities, the brightnesses that these stars achieve in log units. They get up to 10 to the 4, that's a 4 up here, 10 to the 4, that's 10,000 times more luminous than our sun. So folks, we are in for real trouble if we're around 5 billion years from now when the sun does the same sort of thing, becomes a red giant, a so-called asymptotic giant branch star. That's what the AGB means here. That's an arcane astronomer's term for it's making a second trip up the red giant branch as it evolves. So we're in for a bad time. The sun's going to be 10,000 times more luminous than it is right now, and its diameter will be something like the Earth's orbit around the sun. So life on Earth will be extinguished. Earth will be perhaps vaporized in this process, which makes this, of course, this story about planetary nebulae maybe that much more interesting if you like scary death stories. So anyway, at that point, when the star has achieved that sort of luminosity and size, its atmosphere is very tentatively held to the core of the star, and it's producing so much radiation that it actually pushes its outer layers away. At that point, you start to see deep inside the star where nuclear fusion has been going on, and the star becomes much hotter. It moves this direction in this diagram, and the phase we're talking about is super brief. Look at the number here. It's 10 to the 3.7 years, so less than 10,000 years, a few thousand years of the lifetime of a star that has been living for billions, about 1 billion years, is spent in this phase where it's throwing its outer layers off. When those outer layers are thrown off, they're suddenly exposed to very hot core. That hot core is bathing the material that's been blown away in ultraviolet light, and it literally rips that material to shreds at the atomic level. It ionizes that gas, and that produces some very interesting results. So, okay, enough about this quantitative trip through the star's life cycle near the end of its life. Let's look at some fun pictures. Okay, this is
Dr.
an image.
Gassner?
Yes, please.
Dr. Gassner, I have a couple of questions here.
Sure thing. Yeah, I meant to say, if you have questions, go ahead and interrupt. Go ahead, Kelly.
Okay, thanks. I'm just going to remind folks to put the questions in the chat box or Q&A.
Right, I can't see them, so it's good that you're.
No, that's totally fine. I'll collect them. It's your discussion on the temperature of the stars as they grow and explode is fascinating. I'm sort of curious about the space between stars. Because you always think about space being ice cold, and the way you're talking about the heat that's generated, how far does that heat generate, or is it sort of encapsulated in an orbit, or not an orbit, around the sphere of the star?
That's a really excellent question. So the Earth is about 93 million miles away from the sun. The sun's surface temperature, as I mentioned before, is about 6,000 degrees Kelvin, 6,000 degrees in the centigrade scale, quote unquote, above absolute zero. Here on Earth, the temperature is a mere 300 degrees or so above absolute zero, and that's comfortable. That's good for life. If you move much further away, things get colder and colder and colder. And it's for precisely what the reasons that I think the question is getting at, which is that the further away you are from the radiating source, the easier it is to take that radiation and re-radiate it out into the darkness of space, the cold space around you. It turns out space isn't completely cold. All of the space around us is at a temperature about 3 degrees above absolute zero, thanks to the Big Bang in which the universe's material was generated. So that's kind of the rock bottom temperature that we can get to. But the further you are away from even these very luminous objects, the colder things get. I hope that answers the question.
It absolutely did. Thank you so much. Please continue.
Okay, sure. Great question. So this is an actual image of a red giant star releasing its outer layers out into the empty space around it. And this is an image that wasn't taken in visible light. This image was actually taken in light that's given off by the carbon monoxide molecule. It turns out that as stars die, stars like the sun, they produce a tremendous, as I was saying before, they've already fused hydrogen into helium, helium into carbon. A lot of that carbon gets mixed out of the interior of the star out into the outer reaches of the star's exterior. And when the star becomes a red giant, it gets pushed out. And the carbon finds oxygen very easily. And once carbon and oxygen bond, they stick together very well as a carbon monoxide molecule. So dying stars, these red giants, dying sun-like stars, are enormous reservoirs of carbon monoxide that's released back into the universe. Carbon monoxide can be broken down eventually and form other things like organic molecules. And that's when, of course, life gets interesting. But I wanted to show you at least one image of the material actually being blown off of the surface of a red giant star. The red giant is not even visible in this image. It's down here inside the inner cocoon of carbon monoxide. And in fact, I forget the exact size scale of this image, but it's much, much larger than our solar system, 10 to 50 times larger than our solar system, our entire solar system. That's the space in which this material is being blown back out into interstellar space when we can still see it in the form of light emission from carbon monoxide. This image was actually taken by the set of instruments that you see down in the lower right. It's a very impressive array of radio telescopes called the Atacama Large Millimeter Array down in Chile, up at an altitude of 16,000 feet in the Atacama Desert in the Andes. And that's one of the most sophisticated instruments that we have to give us images like this in the light of carbon monoxide. It was obtained at radio wavelengths, out at a radio wavelength of about 1 millimeter, the light that's coming from the carbon monoxide, that is. So this is the material that's coming off of the red giant star. Once the interior has been exposed and the core of the star starts to become unveiled by this process of the mass being lost, the envelope of the star being ejected, then you can get an object like this. This is a classical planetary nebula, IC 418 is what it's called. And this is a Hubble Space Telescope image. You see the Hubble down there in the lower right. This is a Hubble Space Telescope image of a planetary nebula that probably started out in the phases just preceding it. I'll go back as a mass-losing red giant star like this one. But once that inner core becomes unveiled and the ultraviolet starts to attack, if you like, the material that's been lost and ionize it, then you start to see light that is generated at visible wavelengths. And that's what the Hubble Space Telescope excels at. And that's how this image was taken. One of the most amazing things, though, to those of us who study a so-called planetary nebula, an object that's in the process of losing a solar-like star that's in the process of losing its outer layers, one of the most amazing things about planetary nebulae is the variety of shapes that we see. So this is one example of a planetary that was imaged by Hubble, and I'll walk you through several in a row here. This is another one. NGC 2392, also known colloquially as the Eskimo Nebula. Then there's this one. This is the Ring Nebula. In a dark sky with a small telescope in the summer, you can look straight overhead with the telescope and point in the right direction, and you will see the faint outline of the Ring Nebula. But this is a Hubble Space Telescope image showing us the rich structure that exists in this nebula. And you can see pretty well, and I think in a couple of these objects I've shown you, here's the core of the star now being unveiled. And that's the object, the white hot object that's now producing ultraviolet light and destroying the atoms around it, ionizing the atoms so that they glow and we can see them with the Hubble. Another one. This is NGC 31, actually it should be 3132, there's a typo in my slide. This is an example of a star that's not just one, but two stars at its center. So now things can get a little bit more interesting because it turns out that stars often travel in pairs or triplets or quadruplets. They're so-called multiple systems or binary systems. And some of those actually will become planetary nebulae when they die. So that becomes an interesting question as to what that might throw into the mix here. Here's also a planetary nebula. Now this, yes.
I'm sorry to interrupt.
No, no problem.
I heard that stars can take energy from one another, or there a larger star can take something away from a smaller star. Do you know what that is? Do you, and is that last photo that you had sort of reminded me of that question?
So
there were two stars traveling, or stars can travel in pairs.
Right, and it is possible if those stars are in close enough proximity that, especially if one of them starts to become a red giant, the other one will start to gobble down material that's lost from the star that started to die. So that is actually quite common, and that gets to something that I'll talk about later on in my talk.
Okay, great. Yes. Well, thank you.
Great question. Yep. Just a quick note, by the way, these two stars are separated by too much for them to have interacted. So they may have nothing to do with each other other than they were traveling through space loosely bound together. But we'll see some examples, in fact, this next one, in which that's probably not the case. This is a planetary nebula. It has a tremendously hot star inside, but we can't see the star. All we can see is the nebula. There's a dense waste of, if you like, an equatorial waste, a band of dust that's blocking our view of the star. So something very different is happening in this object. It's called the Butterfly Nebula, and I'm going to be talking about it a lot in the rest of the talk. So I've just shown you a wide variety of structures here in terms of these planetary nebulae. What happens when a sun-like star, a star maybe up to 8 times the mass of the sun, what happens when that star runs out of nuclear fuel, becomes a red giant, casts off its outer layers, and begins to die? We see all variety of shapes here, from what look like round nebulae to sort of elliptical shaped nebulae, maybe barrel shaped nebulae, and then all the way to things like the bottom center there where you see the Butterfly Nebula, and the one to its left, which is called Hubble 5, named for Edwin Hubble, who probably discovered it, which is also a very odd bilobed pinched waist nebula. So how do the nebulae get these shapes? Well, what one of the questioners just asked is key to this whole process, and that is, if a star has a friend, a lower mass star that's orbiting that star, when the first star begins to die, it's used up all its nuclear fuel, it will begin to dump material onto its companion, and that can generate a geometry in which the second star can begin to lose mass, or at least govern the direction in which the mass is lost. And that can get even more severe if the first star expands into a red giant and actually swallows its companion. That can happen. That's a so-called common envelope process, where the two stars actually merge together and they share the first star's envelope, or its extended atmosphere. When that happens, bad things can happen on a very short time scale. The outer layers of the star can be ejected, ripped off very quickly. And we can get all kinds of bizarre results from that process. So by studying planetary nebulae, we think we can start to get at this process of what happens when two stars are close enough together that they can interact with each other. My colleagues up the road at University of Rochester, have produced a very sophisticated set of simulation tools. They can put in the real physics of what happens when a star becomes a red giant, begins to blow off its outer layers, and then say, because it's interacting with a binary companion, a companion star, the mass loss process becomes collimated, becomes focused. If you just have a single star, you might expect to see something like what's shown here, where the fast impinging of this shell of gas is due to primarily the fact that you're seeing the inner layers of the star being peeled off, and the mass is being ejected faster and faster, and eventually kind of piles up like a snowplow. And that's this spherical shell that can develop. If you have a single star. If you have a second star, so that the second star can start to affect the direction in which the mass lost from the first star happens. Then you can get a jet forming perhaps. And out of that jet, you can get a very different geometry in the shape of the planetary nebula that results. You can even combine spherical mass loss and jets, which could happen in some systems, and get intermediate sorts of nebulae that have properties of both a very collimated, tightly focused mass loss and a more spherical mass loss. So you can get all of these configurations, and we don't quite know which process is going to win out. We can produce simulations, as you can see in our computers, that can predict what might happen, but what does happen? That's the question. So that's what we want to know. We want to know it. One of the ways we can try to figure it out is via observations with the Hubble Space Telescope. The Hubble Space Telescope has been a real engine of discovery for planetary nebula research. All the images that you see here on the left were obtained by the Hubble. You see it here in orbit, a picture that was obtained by one of the servicing missions that was performed by the shuttle program. And one of the last missions of the space shuttle was to put in a new camera, a then new camera in 2009. This is called the Wide Field Camera number 3. It was the third camera in a series. Well, there was one camera that was actually fixed that became camera number 2. And then this was a third camera in a series. And this one was particularly powerful because of the wide wavelength coverage that it provided, all the way from the ultraviolet, so wavelengths shorter than the eye can see, to the infrared, wavelengths longer than the eye can see. But we noticed that we're getting on in the third decade of Hubble's lifetime, and well into the first decade of the use of this new quote unquote camera, the last camera that was installed on Hubble. It can't be serviced anymore because the shuttle program is no longer with us. So the instruments on Hubble are the instruments that we have for perpetuity now. So this Wide Field Camera 3 had actually never really been used to its full potential to look at planetary nebulae. So this is what motivated, I'm now going to transition to the research that we're doing at RIT in the next 15 minutes or so, last 15 minutes or so of my talk. The work that we've been doing involves imaging with the Wide Field Camera 3. And it was motivated by the fact that nobody had really done a good job, the right kind of a job on planetary nebulae using the Wide Field Camera 3 in its full capabilities from near infrared, from near ultraviolet all the way out to near infrared in terms of wavelength space. So we picked 2 planetary nebulae that I'm particularly fond of for various reasons. They're just very interesting objects for all kinds of reasons. They go by very prosaic names of NGC 7027 and NGC 6302. They are the number 6302 and number 7027 in the NGC catalog. And that's a catalog that's used by astronomers that is used to keep a record of nebulous objects that are not stars. So NGC 7027 has been imaged multiple times by the Hubble Space Telescope, but never with the Wide Field Camera 3. It's about 3,000 light years from us. We think that it started becoming a planetary nebula. Its outer layers started to become ionized and ejected about 1,000 years ago. So as planetary nebulae go, it's very young. It's just in its beginning stages as a planetary nebula. The central star, though, has already heated up. We can see now the interior to the point where the central star is about 200,000 degrees. Along with the central star of NGC 6302, this is one of the hottest stars known to humans. And not only does this object have sort of a rich structure that you can see in this early Hubble Space Telescope image, or it's actually an overlay of color images, but it also has a tremendous amount of molecular gas left around it. It has molecules. So it has the raw materials to form life that are being thrown out back into interstellar space. As I mentioned, it's never been imaged. It had never been imaged before with Hubble's Wide Field Camera 3, despite the fact that that camera had been on the telescope for about a decade. This is the other one, the Butterfly Nebula, which is an iconic image from Hubble. And this nebula is just a little bit further away. than the one I just previously showed you, 7027. It's maybe twice as old. It's about 2,000 years old in terms of when it started to become a planetary nebula, when the central star became hot enough to start ionizing the material that it was losing. And if anything, its central star may now be a little bit hotter than NGC 7027's central star. It also has a tremendous amount of molecular gas and dust embedded in this nebula that's otherwise ionized gas. And actually, this is one of the first objects that the Wide Field Camera 3 obtained images of when it was first installed. But there had been no imaging of this object by the Wide Field Camera 3 in the last dozen years or so. So we set out to set all that right. And I'm sort of showing this here, this eye chart of a table here, just to give you some overview of the sort of things that we threw at this pair of nebulae using the Wide Field Camera 3. We used filters ranging from the ultraviolet, and these are actually showing the wavelengths in nanometers at which these images were obtained. So 243 nanometers and 343 nanometers. These numbers are meaningless really until you compare them with human vision, which starts around 350 or 400 nanometers. So this is just short of what the eye can see. And then we moved all the way through the optical, through all these different wavelengths, into the near infrared. And now we get to filters that are encoded in microns, as 1.28 microns, 1.3 microns, and so on. So now we're getting out to wavelengths that are 2 to 3 times longer than the eye can see. And over here in the right-hand column, you see the different elements that we were targeting with these specific filters on the Wide Field Camera 3 and the Hubble. These are lines of highly ionized neon, lines of highly ionized oxygen, somewhat ionized sulfur and iron, and lines of hydrogen. Fundamental transitions, these are, of these different elements. And we thought by looking at all these different elements and all these different wavelengths of these elements, we're going to see a wide variety of phenomena going on in these nebulae.
So Dr.
Kastner, sorry, go ahead.
If you could go back to the previous slide.
Sure thing.
So when you're looking at these images from the Hubble, is it true color that you're actually seeing, or is it the filters that are creating the colors, or is it the substances that are creating the color, and where's the light coming from?
Great questions. Okay, great questions. I think I'm about to answer them, but we will see. So hold that thought. If I don't answer those questions, we should definitely come back.
Great, thank you.
Sure. So I was just about to show you the images, and each of these images was obtained within a single filter. So it's really isolating a single wavelength. These are false color renditions where we're showing the intensity of the light in the color scheme that we're using. So in each case, it's the intensity, for example, of neon 5, and this is the intensity of hydrogen in its hydrogen beta transition, and the intensity of oxygen 3. By the way, this neon 5 oxygen 3, this is astrophysicist nomenclature for neon 5 is 4 times ionized neon. Astronomers always do things in weird ways. But this means that 4 of the electrons that would ordinarily orbit a neon atom have been ripped off, and we're seeing neon in that ionized state. So that wavelength isolates neon in that particular state of ionization. Same with the oxygen. This is hydrogen in its neutral state after a proton has found an electron and recombined, in the case of the H beta and the H alpha images. And this is nitrogen singly ionized and sulfur singly ionized. So those are the images that we got in the ultraviolet and visible. These are the images that we got in the near infrared. And if you just kind of look through this set, you'll see that the nebula changes character as you look through these different images. So thanks to having all these images, and this is again a false color rendition of each of the images that we obtained in these filters. Thanks to having all those images, we can begin to combine them by color coding them and then looking at the color coded image. So that's what we're doing here in this image. I've picked 3 filters here. that span the wavelength range all the way from the ultraviolet, that's the F343N filter, which isolates a wavelength of 343 nanometers. Again, that's highly ionized neon. And then we've color coded the 502 nanometer image, which is oxygen 3. We've color coded that green. And then we've color coded the 1.28 micron image, which isolates hydrogen. We've color coded that red. So as you look through, if you look at this image and you're looking at the different filters, you're seeing the different elements glowing, which is partly a result of where those elements happen to be in the nebula. And it's also partly a result of how efficiently those elements are being ionized. So they're glowing because they're absorbing ultraviolet light. So it's a combination of those two processes. And it's not always obvious which is the more important effect, where the element is or whether that element is being excited, whether it's being ionized. You have to take both of those important factors into account in order to understand in astrophysical sense what we're seeing here. But I hope you agree this is a pretty picture. It's really fun to see how the different elements show up in different areas. The different excitation of these elements shows up in different areas in this object. And one of the things that was striking to me when I generated this image was the fact that you're seeing the hydrogen, you see these deeply embedded in these clumps, and you're seeing for example, the oxygen and the neon more on the front surfaces. And that's really a result of the fact that the oxygen and the neon is showing us where the ultraviolet light is hitting the clumps of gas that are glowing in hydrogen as well. So that's one example of what we can look at. Here's another example.
Clumps of, excuse me, are those clumps of gas, are they constantly moving?
Yes. So
capturing this is pretty significant.
Okay, so they are moving, but this object has been around for a couple thousand years. We've now imaged it twice with Hubble in 10 years. And I'm going to show you an image in a little bit that will show you that we can see the differences. We can see the changes in that time. They are moving, but from our vantage point here on Earth, this object is very far away and it's very big. When I say very big, its span, a wingspan you're seeing here, is more or less the distance between nearby stars in the solar neighborhood. So it's a very large object. So when you see it over a 10-year period, you're watching it change very slowly, but perceptibly. You can see it change. Those are great questions. So this was the image, by the way, that really knocked my socks off when we got it, because I really didn't expect this to be the case. It turns out that iron, the light from iron, as it's being ionized, looks completely different in this nebula from everything else that's been imaged so far. Iron seems to trace this kind of S shape through the nebula, with some other small pieces, chunks of the nebula, you can see sort of these dark regions that are also being illuminated. Turns out this line, this particular wavelength that iron gives off, is very good at finding regions in which gas that's slowly moving is being hit by gas that's very fast moving. So we think what this is telling us is that there's a fast outflow from the region of the vicinity of the central star that's hitting material that was ejected when the star was a red giant, much earlier in its recent past. So we are watching this nebula being actively shaped right now when we look at this emission from this so-called iron 2 line at 1.64 microns. So I think others agreed these images were pretty. They made the astronomy picture of the day, and this lovely color-coded Hubble Space Telescope montage from our images was generated by one of the masters of this process of combining images into color overlays, Judy Schmidt, and made the astronomy picture of the day last summer. And we were very proud of that, of course, and it was a lot of fun to see the tricks that Judy could play. You're seeing the nebula turned over on its side here just because aesthetically it's kind of nicer in this configuration. This is yet another way to look at the nebula, though. You can start to take ratios of the images that I've just shown you. And when you do that, you're starting to see regions in which certain elements are enhanced over other elements, and their ionization is enhanced over other elements. And so we've taken three combinations here. One of them, this in the red here, actually shows us very effectively where the dust in this nebula is, because that particular ratio of two different emission lines of hydrogen is very sensitive to the absorption of light as it's passing out of the nebula. So we're seeing a tremendous amount of absorption from dust in the very center of the nebula here. Take a quick sip of water. We're also seeing regions where the nitrogen is lighting up very brightly. It turns out this is one of the most nitrogen-rich nebulae that is known in the world of planetary nebula. So it's very likely that this star was ripped apart at a point in its lifetime where it had generated plenty of nitrogen. And in fact, a lot of the nitrogen in the universe may be generated in objects similar to this one. And again, you see the ionized iron that's tracing a completely different shape. And this is the image I was talking about, the image overlay I should say that I was talking about, that is going to show us the motion in this object. So this is a different sort of color overlay, again, from 3 near-infrared images that we took with Hubble. And if you zoom in and you look at the image that we got at 673 nanometers in 2020, earlier this year, compare it with last year, about a year ago, I should say, and compare it with the image that was taken in 2009, you can now see motions in the inner nebula. The arc that you see here, that's 2 different images subtracted from each other. The fact that it's white on one side and black on the other side means that this shell of gas has actually moved out in those 10 years quite significantly. And another thing that we noticed about this object had been previously identified as the very likely central star of this nebula. But when we looked at it in 2020, it was significantly different in position. It turns out this is just a foreground star that happens to be passing through in front of the nebula. It's probably 10 times closer to us than this nebula. In fact, these expanding bubbles that we see on either side appear to be indicating where the real position of the central star is. We can't see it. It's buried inside that dense torus of gas and dust that was showing up in the form of the red emission that I showed you in the last image. Okay, I don't want to blather on too long. This is that color image again that Judy Schmidt produced, but I will very quickly walk you through the other nebula. Oh, sorry, okay, that's my overlay of the image that's showing the distribution of dust extinction, the distribution of ionized nitrogen, and the distribution of ionized iron. So you can sort of see how it overlays. And looking at these objects and these different emission line ratios is very powerful. Is a very powerful way to literally dissect these objects and understand what's going on in their interiors. So this is the other object. I'm going to run through it more quickly, unfortunately. NGC 7027. Again, these are the two. The set of a dozen images that we got of this object in the 12 different filters, shown in 2 different magnifications, where we're zooming in more on the right-hand panel. So you can see, in fact, the central star in NGC 7027 is detected. You can see it right there. That's the hot 200,000 degree central star. And this nebula, again, as you move through this image set, you can see it changes character, maybe not quite as radically as the Butterfly Nebula, but it does change character. And now you can take all those images, and as the questioner earlier wondered, you can color code them appropriately and recombine them. This is an image that was put together for us by the staff of the Space Telescope Science Institute, which is the institute that operates Hubble and runs its science program. And they did a bang-up job of showing us the 3-dimensional view, really, of this nebula that you can get when you overlay these images. So a student working with me that I mentioned before, Paula Moraga, is hard at work on understanding the line ratio, what the line ratios can teach us. And I just really love this image that she was able to produce, where you see the different aspects of this nebula popping out in such such vivid fashion. The red is again showing us dust extinction. The green in this case is showing us where the ionized sulfur is showing up. And the blue is showing us again where the ionized iron is showing up. And just like NGC 6302, it's only showing up along this one direction. And that's obviously pointing out to us where the fast moving material coming from the central star is ramming into the slower moving material that was ejected when the star was still a red giant. So this is an object that's actively being shaped as we watch. And it's being shaped in ways that may have to do with the binary nature of this star when it was living its normal life, burning hydrogen into helium in its core. There's a long literature now of what happens when you have two stars that are orbiting each other and one begins to lose mass rapidly. And the likelihood is you get a spiral pattern showing up. We saw it earlier in the image that I showed of the star that was imaged by the Atacama Large Millimeter Array in carbon monoxide. And we may be seeing it again in NGC 7027. You see the image on the right here that we obtained with Hubble. It was put together by Space Telescope. And on the left in the middle, you see a simulation of what happens when two stars orbiting each other are so close together that when one star becomes a red giant and begins to engulf the other one, then they actually merge and form a common envelope. And that process probably produces this sort of spiral pattern. And it can also produce rapid mass loss, rapid mass ejections, some of which can go off in random directions. And that also seems to be what we see in NGC 7027. So I'm going to leave you right there with these pictures that, again, Space Telescope Science Institute and Judy Schmidt were able to put together from the image overlays that they produced from our image set. And I will happily take your questions. You've already asked me some great ones, but I'm happy to answer some more.
Thank you so much, Dr. Kastner. I'll wait for some folks to populate with questions, but we did get one big exclamation of the Pink Pillow nebula.
The Pink Pillow nebula.
I think it was a shot. They were just calling that. We did a question from Vasuki Sachdari. How does the upcoming launch of JWST impact your research?
I love that. It's a great leading question. Well, guess which, I guess I can safely say this now. The JWST Cycle 1 proposal review has actually already taken place. Proposals were submitted last fall, I guess. I'm forgetting the exact time frame. Or was it more recent? Anyway, all of us at RIT were the astrophysicists who are the observational astrophysicists at any rate, we're all going nuts because we were all working on James Webb Space Telescope proposals. And as you might imagine, I was very interested in what James Webb Space Telescope could do for these two nebulae. So guess what? I have submitted a proposal, and my hope is that we can do the same sort of intense coverage of lots of different wavelengths. James Webb Space Telescope is an infrared optimized telescope. It's bigger than Hubble. It's about 3 times, well, not quite, 2.5 times the size of the Hubble Space Telescope in terms of its diameter. But it's going to observe at infrared wavelengths, beginning with the sort of cutoff where you saw with the wide field camera, about 1 or 1.5 microns, and going all the way out to a wavelength of about 28 microns or so. So it's going to be covering a part of the infrared wavelength regime that really hasn't been well explored yet, and especially not with a telescope that size, because it's going to be above the Earth's atmosphere. The Earth's atmosphere is very good at absorbing infrared. So by using James Webb Space Telescope, we really hope we're going to be able to get a look at these same nebulae, but in infrared light, which is very good at penetrating dust. So we may finally be able to see, for example, where the central star is in this mess of the waste of NGC 6302, among many other things. That's a great question.
So when JWST is launched, will Hubble be decommissioned, do you think?
That's also a great question. And the hope is no. The hope is that the two of them can operate in parallel for some time. So Space Telescope Science Institute is going to be responsible for operating both telescopes. And that's both great and also a problem in the sense that there are only so many resources one can throw at the operation of these major missions. So the hope is that both of them can operate for quite a while. Hubble is aging. It's not getting any younger. If it loses more gyroscopes, which are actually allowing it to point accurately, then it could be no longer useful. So as long as Hubble is useful, the hope is it'll keep going. And I'm knocking on wood here. It could be another decade or so, money and equipment permitting.
So I have two last questions that have popped up. The first one is, in taking these images from the Hubble, how far is the Hubble from the nebulae when they're taking the photos?
So the Hubble is orbiting the Earth every 90 minutes. So the Hubble is tied to the Earth, if you like. And these two objects are a few thousand light years away. So the Hubble is basically our eyes, but just above the atmosphere. It's essentially the same view that we have of these objects.
And then we've got a question on the correlation between strength of iron emission and age of planetary nebula. There is one.
Yes, that is perhaps the subject of our next Hubble Space Telescope proposal, because I think we're learning a lot about how young these nebulae are and how they're being shaped by looking at that emission line of iron at 1.64 microns. So we intend to look at a good deal more planetary nebulae in that same line with Hubble so that we can see exactly where the shaping is happening now. It's a great question.
Well, Dr. Kastner, I think that's all the time we have for questions. Do you have any parting thoughts that you'd like to share with us?
No, just that I really do appreciate the feedback and the great questions. As you can see, most of those questions were sort of like maybe people had seen this talk before. They were anticipating exactly what the sort of science is that we're trying to do with these images. So I really appreciate the conversation.
Oh, great. Thank you to our audience, and thank you to you for sharing your passion and knowledge with us all. All audience members will receive an email from us within a week with the links to today's webinar recording. Thank you to our interpreters, Nick and Jen, and our live captioner. As a reminder, these Tiger webinars are available on the RIT Alumni Association YouTube site. The link's in the chat box, so feel free to catch up on past events. You can view a full listing of upcoming events at our website, www.rit.edu/alumni/events. We have several each week, and we'd like to include you in as many of those as possible. You can please exit the webinar by simply closing your browser window. Please do let us know what you thought of the webinar through a brief survey you'll receive via email. Have a wonderful week. Stay safe, stay positive, and stay your course. Thank you. Oh, we got a thank you.
Yeah, I was going to look at the chat. I wanted to see there's some nice comments there.
And just so you know, yes. I think the people that were attending this webinar, oh, there's a whole bunch here, yes. Probably were much more well-versed than I. And so a lot of the questions that I came up with on my own. So,
they were good ones, Kelly. I really appreciate it.
I never saw this presentation. I didn't have a chance to look at it. So you know, it felt like I had a crystal ball because you started to answer the questions like almost immediately. I thought that was wonderful.
Yeah, well, that's one of the fun things about giving a talk like this. You know, I have lots of you know, I have lots of students in my class this year, and I find that the sorts of questions I'm getting are forcing me to think very carefully about what assumptions I'm making, you know, about what people might know and not know, and so on, and the way they're thinking about the same material that I'm trying to show. So it's great. It's great.
It's the sophistication behind this is just mind-boggling. And I think I'm now very afraid about 5 million years from now, or
Oh, 5 billion, 5 billion.
yeah, 5 billion years from now.
Okay.
And I keep thinking we're not working fast enough. We really need to get out there. We really need to find something for future generations. And just the way you described it about the sun growing as large as the Earth's orbit, I just keep seeing it sort of suck up all the planets. And
right. It's mind-boggling. Absolutely. Yeah.
It is. It's just astounding. Right. But again, thank you so very much, and thank you to the audience for hanging around. And I'll be touching base with you over the next week or so.
Sounds great. All right. Thanks again.
All right. Have a lovely evening, one and all. Take care.
All right.